here is the way that we are dealing with decidable and undecidable rules. Data flow analysis is a pretty widespread method. So we got a number of analyzers. We are focusing on, these are language dependent. We focus specifically on the C and C++ language. And these analyzers, they take care of checking, of tackling decidable rules. Incidentally, you may have decidable rules which are unscalable. So then you get the same problem of trade-off between false positive and false negatives. But as it happens, MISRA C, all the decidable rules are also scalable. 100% enforcement can be guaranteed. And the problem is then when you've got to deal with undecidable rules, what the analyzers do, they pass semantic information forward to data flow analysis. And data flow analysis deals with undecidable rules. So data flow analysis is based on asking certain questions to SAT solver and SMT solver. SAT solver are about solving the problem of Boolean satisfiability. So if you got a Boolean expression which is composed of a number of variables, a number of Boolean variables, it's easy if you know the value of the variables to know what the value of the expression is. But if you ask the question, can I give the variable certain values for which the expression is true or for which the expression is false, that is a very hard and unscalable problem to solve. And so that means that SAT solver is affected by problems of resources, memory consumptions and time consumptions. And what this tells you is that when you've got an undecidable rule, you are pretty much affected by resource problems. And you need to deal with the resource problems, you need to find heuristic algorithms. On top of the SAT solver, which deals with Boolean expressions, you got SMT solver, which also uses the SAT solver, but to address problems, theories which are about integers and floating points and various data structures such as lists, arrays. And on top of that, in between the analyzers and the solvers, there is data flow that on one side receives semantic information and on the other asks questions. And the way it deals with that, that's where the undecidability lies. Looking at data flow messages we are generating, we have different categories. For each message, we got different categories. So when we are sure about a problem being there or a rule being violated, we provide either a constant or a definite message. If we don't know whether we cannot exclude that a problem is present, we generate a possible message. And then there are some intermediate degrees where we are more confident that there may be a problem than not. So the apparent and suspicious represent different degrees of confidence. So if you look at these categories in the spectrum that goes between sound and complete, if someone wanted to use the tool in a complete manner, so only address problems that are definitely there, then disable all the messages except for constant and definite. If the user wants to use the tool in a sound way, then enable all the messages and look at everything. Or there can be also intermediate choices. And besides all these messages, of course, you've got what we've seen before, the problem with resources, and there are messages about timeouts and memory that also indicates when resources are exceeded, and in some cases, simplification of the code. Again, developers' discipline can help solve not all of the situations, but a few of them. Here is in particular a simple example of how data flow works. you got a function path where there are three possible paths that the execution can take. If you see if x is equals to 0, then z is initialized to 0, and by the time it gets to the division, there is a division by 0. So there is a problem, and there's something which is apparently wrong with this source code, so it's likely to be an error, and therefore we generate the apparent message. On the middle, you can see the question, the kind of questions that the data flow asks to the underlying SAT and SMT solvers. And based on those questions, then it decides which messages, if any, to generate. And the bottom example is about the loop function. If you, for instance, you call this function with a negative value, then for x, then z remains 0, and you've got again a division by 0, but that's not clearly as apparent as the earlier, so you will have a suspicion message in this case.